In this lecture, we will discuss various forms of serial communication. So what is serial communication? The main idea in serial communication is that data bits are sent sequentially in time instead of on parallel wires. What's the motivation to do that? Well, usually the most driving motivation to do that on a board is to reduce the pin count. When we are trying to interface with a device, it's very easy to create a very complex device inside a chip. But to actually communicate with that device in and out of the chip, it's pretty inconvenient to require lots and lots of pins. There's another problem with having lots of pins. So imagine we had lots of pins and we needed to run multiple electrical conductors in parallel. Well, each of these electrical conductors generates a magnetic field around it. And that magnetic field in turn induces a current in neighboring conductors. And that is what we call electromagnetic interference. So one of the problems with parallel buses on a board is that they create electromagnetic interference. Yet another problem is a bit more subtle. So imagine we have a bus and it goes around an angle like this. Well, obviously this wire in here on the inside is a lot shorter than the wire on the outside. As our communication speeds get higher and higher, the distance traveled per unit time by an electrical impulse starts being a significant factor. So, at several gigahertz, the distance traveled by a single waveform in a cycle is on the order of centimeters. And that means that the change in length for different wires on a bus can actually cause synchronization issues. But the real reason you guys will need to deal with serial communication is because this is what's used by many of the devices we see. So what will we cover today? First, we'll cover the basic idea of a shift register. This is the most basic kind of serial communication. It's rarely used, but it's important for understanding the other forms of serial communication that are built upon it. Then we'll discuss what is usually referred to as serial. Universal asynchronous receiver and transmitters, UARTs, are used in many devices and are a very common form of communication between embedded devices. Then we'll cover two important buses that are used to communicate between devices on the same board, the SPI bus and the I2C bus. I will also mention the RS485 bus, which is a form of serial communication that's used for longer distances and is often used in industry. And I'll mention perhaps the most important serial bus we have today, which is the Universal Serial Bus, USB. So what happens in a shift register? Well, let's try and encode 3 characters, SER, using a shift register. So we'll use the ASCII encoding, and although most of you think of ASCII encoding as being a byte encoding, it actually isn't. The ASCII code is a 7-bit code rather than an 8-bit code. And the bits representing the characters S, E, and R are the bits you see here. So this will be capital S, lowercase e, lowercase r. What will happen on the wire is that we will be sending these bits clocked out using a clock. So the clock, every cycle of the clock represents the transmission of a single bit. And the upward transition of the clock, in this case, marked by these vertical gray lines, indicates the time at which we want to latch the voltage on the line that indicates what that bit was. So what the line will actually display on your oscilloscope, if you look at it, is what you see here. And that is provided that you synchronize your viewing with the clock. What's very good about shift register is that they're very efficient. Basically, every bit transmitted on the line is a data bit. So they are 100% efficient. But there are pretty significant disadvantages as well. So imagine what happens if we lose a clock tick for some reason such as interference. Well, our communication gets completely desynchronized. We have no idea where our ASCII characters are starting, and we have no way of recovering that synchronization. So synchronization loss is one important reason people don't often use shift registers. Another limitation of shift registers is that there is no way to designate a transmitter and receiver. So shift register connections are always simplex connections. There's one designated transmitter who's pulling the voltage up and down, and a designated receiver who's getting the information in. Now UARTs are what we usually refer to as serial buses. The universal asynchronous receiver and transmitter does a whole bunch of nice things. Unlike shift registers, which require a clock, UARTs are asynchronous. We can send data on them when we have data, and there's a way to not send data. Let's imagine we're trying to send two characters, S and asterisk. These two characters have the ASCII codes you see here. However, one of the weird things about UARTs is they send the bits in reverse order. So the lowest order bit gets sent first, and the highest order bit gets sent last. So we're going to have a 7-bit signal. But let's assume for now that the serial bus we're using is a 7-bit, 1 start bit, 2 stop bit, even parity bus. What does this mean? Well, the resting state of a UART bus is high, as you see here. Now, whenever data is beginning to arrive on the bus, we always send the start bit. The start bit pulls the bus down for 1 bit duration. Then we send the data. And after we send the data, we send, in our case, a parity bit. Now the parity bit is a bit which is set to 1 or 0 in the case of even parity to ensure that the number of ones was even. So since we had 4 ones already, 1, 2, 3, 4, the parity bit has to be 0. And after the parity bit, we send 2 stop bits to signal the end of our byte. So what would happen for the second byte? Well, we have our start bit, we have our data. This data had 3 ones, so to make the number of ones even, we need to add a 1 and then follow by 2 zeros, and then we let the line relax back up to high. So what's the efficiency of this encoding? Well, we sent out 11 bits, but only 7 of them were data. So it's only about 64% efficient. You can usually have duplex UARTs. So usually there are 2 channels, one going in each direction. So UARTs are often duplex. You can also run them in half duplex. So if the receiver can put its input on high impedance, then both sides of a UART channel can pull the line up and down. But there's still an issue of flow control. So if I am sending data asynchronously, what happens when your buffers are full and you aren't ready to receive more data? Well, this problem is resolved either by having additional clear to send and request to send lines, so that's the CTS RTS, or an additional form of flow control is called X on, X off. X on, X off doesn't actually require additional lines. In fact, X on, X off is still in use, so any of you who have used a Unix terminal on Linux, for example, might have discovered that if you hit Control S, the terminal stops printing data and freezes. And when you hit Control Q, it resumes scrolling. Control S is the X-off, stop transmitting character, which tells a serial terminal to halt. And X-on is control Q, and it tells the transmitter that it can resume transmission. So serial buses, universal serial buses, usually have either additional lines using CTS-RTS or higher level control using X-on, X-off, sometimes also called software flow control, or they have no flow control. In addition, the UART standards define standard error conditions. UART errors include overrun error, which means that the receiver got a byte before the previous one was read. Underrun error, which means the transmitter has no byte to send. Framing errors indicate that the stop bit is missing. Parity error indicates that the parity is wrong, which usually means that one or more bits were corrupted. And in addition, very importantly, there's the ability to send a break. Why do we have breaks? Well, one of the clever things about the UART design is that the idle form of the line is high. So if for some reason a wire breaks, the idle line will drop low. There will be no one pulling the voltage up. Breaks are indication either of a physical break in the wire or a form of signaling between two serial devices that want to tell each other something equivalent to lines connecting and disconnecting. And back in the days of phone modems, breaks were used to indicate ending calls or starting new command sequences. So how do we use a UART? We need to set the clock to the correct baud rate. It's usually okay if it's a bit high. Why? Well, how much synchronization error will we encounter in what is at most 12 bits? Which means that we can certainly tolerate a clock that isn't precisely synchronized between the receiver and transmitter, as long as the error is on the order of 5% or so. The baud rates are actually limited to very specific values, and most devices either use a multiple of 75 or a multiple of 57600. 75 was the baud rate of old teletypewriters, and as people doubled the baud rate of that higher and higher, we have powers of 2 times 75. And 57600 is the channel capacity of a phone line. And this is why these are the two baud rates that you usually encounter. In embedded system, the clock rate is usually created by using a clock divider on some fast clock inside the system. So it's pretty common that you'll see in the spec sheet of an embedded device the numbers that you need to put into the divider to create the standard baud rates. In principle, UARTs can have 7, 8, or 9 bits of data transmitted in each word, but it is almost always 8 bits, 1 start bit, 1 stop bit, no parity. This is pretty much always the standard that people use by default for UART control. People typically use no flow control for 2-wire buses and hardware flow control for 4-wire buses that have the clear to send and request to send. Software flow control is rarely if ever used. Now let's switch gears and talk about the serial peripheral interface. This is the first of 2 buses we'll discuss, which is likely to be used in any kind of embedded application that you build. SPI is a very common way for external chips to communicate to a microcontroller. And like the original shift register we discussed, the SPI interface is a synchronous interface. And this means that someone is sending a clock that's driving bits across the bus. Now, SPI is a master-slave architecture, and each SPI bus has a single master in this figure, the master is in blue on the right. And what happens is each master and slave pair form a ring shift register. That is, the output of the master's shift register goes into the slave's shift register, and the output of the slave's shift register goes into the master's shift register. The standard names for these connections are master output slave input and master input slave output. And so by connecting the clock and these two lines, we get a high-speed shift register communication. And by having this sort of ring structure, the master can force the slave to send back a copy of the master's message that was received, and in that form validate that the correct message was received. But SPI often allows us to run multiple slaves with a single master. And this is done using slave select pins. So here they're in black. The slave select pins are usually inverted in terms of their logic. And what they do is a slave that is not selected puts its outputs in floating or high impedance mode. What that does is basically prevents that pin from either sourcing or sinking current, and it doesn't interfere with the communication of other slaves with the master. Now, unfortunately, SPI has been used so broadly that there are many, many variants out there, and you need to watch out for them. And usually they're described in terms of the clock polarity. So are bits supposed to be registered on rising or falling edges of the clock? And which direction is data going? Is it going from master to slave or slave to master in each phase of the clock? So there are four different clocking variants described by the clock polarity and the clock phase, sometimes referred to as CPOL and CPHA. Now, SPI can run very fast. Typically, it runs between 25 and 50 megabits per second, which means it's only usable on high-quality PCBs that don't have a lot of electromagnetic interference. Usually, you want the chips to be pretty close together, and one of the big limitations is that slave devices on SPI can't throttle the communication. So basically, the master can send data to the slave at any time. The whole notion of addressing on an SPI bus is out of band, using separate lines, the slave select lines. And the typical applications you see for SPI devices are things like I/O expanders. So for example, if I wanted to add 200 GPIOs to my embedded microcontroller that doesn't have the pin count for those, I could find and daisy chain multiple SPI GPIO expanders and communicate with all of them over a single SPI bus. Another typical application is serial memories. Those are memories that communicate data out in serial fashion. So with a very small pin count, you can attach a pretty large memory to an embedded controller. And these are often used to store data that needs to be loaded on boot. You also see chip-to-chip onboard communication, often done with SPI. Some things to watch out for as you're using SPI. SPI doesn't have a fixed message size. So different devices will use different message sizes, and those sizes are often not even multiples of 8 bits. You can daisy chain devices to store longer words if you're using memory, if you're using SPI for memory. So imagine I have 2 SPI memory devices, each of them storing a byte. If I just connect them in sequence so that their shift registers feed into each other, I can effectively store a 16-bit word. Another important thing to do when you design your SPI bus is to make sure that you have termination resistors on SPI bus output and the correct termination is a 22 ohm termination. Sometimes chips will have internal termination and sometimes not. You need to check that. Also, check whether the devices you use can be on a bus or need a dedicated SPI. Some devices aren't able to put themselves in high impedance mode, and their slave select merely turns them on and off, but doesn't allow them to share the bus with other SPI devices. Now we'll move on to discuss a much more complicated and interesting bus, the I2C bus. The I2C bus is extremely popular because it's a two-wire bus that provides many capabilities. It has a multi-master ability, so multiple devices can master the bus. Devices can be addressed. It is 8-bit oriented, it's designed to send bytes, and it's supported by virtually every chip manufacturer out there. Now, I'll spend a little bit of time talking about I2C and some of the low-level structure of I2C to give you a sense of what you can actually expect to see on a real-world serial bus if you attach your oscilloscope to those pins. And believe you me, when you're debugging your circuit, you will end up doing this. So, because the I2C bus is so popular, there is a website dedicated to the industry consortium that supports it. That website is at i2cbus.com. Unfortunately, last time I looked at the website, the standard itself, the link to the I2C standard, was broken on the website. You can find the actual standard on the website of the company that originally created it, NXP, previously known as Philips Semiconductor. So let's look at what a complicated I2C bus architecture on a board might be. In this board, we have multiple microcontrollers. We have here maybe a microcontroller communicating via an 8-bit parallel bus to a dedicated I2C bus controller. And here, some other microcontrollers communicating via a hardware bit banging interface where they actually generate the I2C communication bit by bit on GPIO pins. Now, each I2C bus here requires its own set of pull-up resistors. So you see that we have pull-up resistors for this bus, pull-up resistors for this bus, for this bus, for this bus, for this bus, and for this bus. But there are devices that can function as a master, selector, and demultiplexer. So this device here allows communication between the buses that it is attached to, as does this device. So the devices on different buses can talk to each other by addressing one another. And then you can have multiple devices sitting on the same bus, and you can extend an I2C bus with bus extenders. And you can also find SPI or USB or UART bridges, which allow you to send traffic to these other buses from an I2C bus. So as you see, you can basically make a really complex hardware architecture with many different devices on a single board using I2C. And this is used extensively in a lot of hardware. So how is this bus designed? Well, there are two lines. One line is called SDA, the serial data line, and the other is called SCL, the serial clock line. Both those lines are pull-up open collector buses. Open collector refers to the kind of design of the transistor circuit that is used to switch the bus, and it means devices can sink quite a lot of current. Now, with a pull-up resistor and an open collector, if any device opens its open collector circuit to ground, the entire bus will go to a low voltage state, to ground. So effectively, this is what's called a wired AND. That is, the entire bus functions like an AND gate that is wired to all the devices. And one of the nice things about I2C is that the architecture defines the levels for high and low as relative to the bus voltage levels. And so some devices have tolerance for higher or lower I2C bus voltages and can be made either robust or low voltage or low current without requiring a change in the standard. So for I2C, low is less than 30% and high is more than 70%. All devices are required to read the line that they are writing to. And the reason for that is that the I2C protocol, as you'll see in just a bit, requires a writing device to be able to read the fact that some other device pulled the line low. Now the data rates that you can see on I2C can get fairly high. You can see data rates up to 3.4 megabits per second in some vendors' devices, but the standard itself goes up to 400 kilobits per second. So pretty much anything that says it runs I2C should be able to run at 400 kilobits per second. So what is the basic line discipline in an I2C? Well, the serial clock line clocks up and down, and when the serial clock is high, the data line is required to be stable. So the timing diagram you see here shows you that while the serial clock is high, the data is stable. When the serial clock is low, change of data is allowed. Now, there are special conditions that indicate start and stop of transmission, and these indications happen by changing the serial data line when the serial clock is stable. If you're pulling the serial data low while the clock is not changing, that's a start condition. And if you're allowing it to go back to being high, that's a stop condition. And the bus master is usually the entity that decides start and stop, but it's a bit more complicated than that, as you'll shortly see. So let's look at the simplest kind of transfer, a data transfer from master to slave. And what I've done here is I've plotted separately the slave's SDA output, the master's SDA output, and the slave clock output. All of these are internal signals that you can't actually externally observe. What you externally observe with your scope are SDA and SCL. So the first thing we see is SDA going low because the master pulled it low. So by pulling it low, the master indicates the start of a transmission. And then the master pulls low the clock between the bits of the address for the device that he wants to address. After he finishes addressing that device, he lets the data line go high. At that point, the slave can pull the data line low, which we see here, indicating an acknowledgement that it has been addressed and is waiting for data. That acknowledgement coming from the slave also gives the slave an opportunity to pull the line low and indicate that it is currently busy and doesn't want to receive the data yet. And it can do that by pulling the clock low. So imagine the master wants to send data. What happens is, as soon as the slave pulls the line low, there is no clock output. And so if the master is also reading its own clock output, it can see that the slave has halted the transmission. And once the slave releases that line, data can start flowing, clocked by the master with acknowledgement bits based on the amount of data being sent. So it could be multi-byte data and have acknowledgement after each byte. And when the transmission is finally done, the master halts the clock and transitions to indicate a stop. So as you see, there are a lot of different kind of exchanges. For example, you can have transmission from master to slave with multiple data, which is what we looked at just now. You can also have a master reading a slave. So here the master sent a slave address, indicated read or write, and got data back from the slave. So here the master leaves the data line high and the slave clocks the data onto the bus using the master's clock. Similarly, you get more and more complicated protocols. For example, the ability to address 2-byte slave addresses, so 10-bit addresses on the bus. And as you see, all of these are defined in the standard, and the standard is fairly complex. So what you usually have is people not writing their own I2C on the bit banging level unless they're doing something very, very simple. Usually I2C interfaces are dedicated chips or dedicated peripherals in a microcontroller. The buses we have discussed so far are local buses. SPI can only span a few centimeters, I2C maybe tens of centimeters, and UART serial connections can typically run a couple of meters apart. But there are serial buses that can handle distances of hundreds of meters. For example, the RS485 differential pair bus. So this is a 2-wire bus, and the recipe for its performance is that the rate in bits per second times the bus length in meters has to be less than 100 million. So for example, a 50-meter bus can run at 2 megabits per second, which is a pretty substantial throughput. Now, one of the features of RS485 is that it has pretty good common mode rejection on its line. So the voltage of an RS485 bus can shift up or down 7 volts around 0, and the bus is guaranteed to work correctly as long as the difference between the D plus and D minus line can be modulated over a range of 5 volts. RS485 buses are terminated with 3 resistors, so they're terminated with 720 ohms above and below, and 130 or 120 ohm between the D plus and D minus line. And the RS485 bus itself transmits the same bits you would expect from a UART, a start bit and stop bits. But it transmits ones by pulling D plus up and D minus down, and transmits a 0 by pulling D minus up and D plus down, as you see in the blue and red scope traces down at the bottom of the plot here. So you should know that if you want to connect devices tens or even a few hundred meters away to your embedded device, you can actually just connect a twisted pair over RS485. However, we would be completely remiss talking about serial buses if we didn't talk about the universal serial bus. It is perhaps the most successful serial standard ever created. It was designed as a peripheral bus, that is, a single host connecting to multiple devices. The general architecture is a tree topology, so a host can connect to a hub that connects multiple devices that themselves have downstream hubs, etc., and so forth. But the communication on the bus itself is controlled by the various hubs and uses time division multiple access. So on a USB bus, every device is given time slots in which it can communicate on the bus. Furthermore, devices define descriptors that describe their capabilities and the channels of communication that they wish to form with the host. So it's an extraordinarily complex standards. There are thousands and thousands of pages of USB standards to read. Back in my industry days, I worked on USB 1.1 devices and knew the ins and outs of USB 1.1 and USB 2, the performance of the first versions of USB was at 12 megabits per second. But if you look at the most recent standard, which came out a couple of years ago in 2019, USB 4 now sends a whooping 40 gigabits per second on the serial bus. And as many of you know from the use of your laptops, USB-C connectors are now used to also carry video for external monitors and do many other peripheral communication tasks that require fairly high bit rates. So if you're curious about the standards for USB, the bottomless pit, which is the standards collection, is at usb.org. And the most recent standard, the USB 4 standard, is at the link at the bottom of the slide. As you see from this review of serial communication, serial standards go all the way between simple shift register-like communication in SPI to tremendously complex and elaborate buses like I2C and USB. It's really important to know about serial buses. It's important to be able to debug them with appropriate tools. I wouldn't suggest to anyone to debug USB without dedicated USB debugging hardware, but simple I2C transactions you could read with a scope, and you can certainly interpret RS-485, UART, or SPI communication with a scope and use that to debug any problems you encounter.